The most frequently measured pressure in the technological field is the atmospheric pressure differential. It is the difference between an absolute pressure and the relevant absolute atmospheric pressure, and it is known in short as the overpressure or gauge pressure. A positive overpressure is referred to when the absolute pressure is greater than the atmospheric pressure. In the opposite case, one speaks of negative overpressure.
In our experiment, we will try to determine the gauge pressure of a system composed by a PVC tube sealed by both sides while water is going out for a little hole. To do so, we will use the Bernoulli equation, the continuity equation, and some of the parabolic shot equations.
This time, this place, misused mistakes, too long, too late. Who was I to make you wait? Just one chance, just one breath, just in case there's just one left. 'Cause you know, you know, you know.
¿Por qué ahora se va tan lento?
70. La presión, eso fue.
O sea, ese está.
¿Y cuántas vueltas usted le tienen a eso?
Yo le digo.
Y sale con más.
No, falta otro, falta otro, falta otro.
Mira.
Falta otro.
Falta otro.
Falta otro.
Es verdad.
So out of this equation, we can get the pressure that's in the pressure that is being exercised by the air, just by taking the atmospheric pressure out, and we get that this equation will give us the pressure here. We expect the pressure here to decrease, as the volume of the air is expanding, and on the cap there's atmospheric pressure that is pushing down the cap, and that's why it imploded. But there's something we need to take into consideration, is that this H is not constant, and we can calculate it like second by second using the following formulas. First, we know that H is equal to volume divided by area, but in this case the volume is changing with respect to time, and to calculate this volume every second we need to take the initial volume that we know minus the lost volume divided by the area. But what happens here is that the lost volume is the flow of water by time, and we need to consider that this flow of water, it is not constant, because the speed of the water going out from here is not constant neither. So there are lots of things to take into consideration that we will now see.
Also, it's important to to say that in the second 30 we have an explosion of our cap, so we have a velocity equals than our first velocity.
Analyzing the data we collected, we want to determine what was the pressure at the time of the implosion of the cap. So we need to know the velocity at that point, which was 1.747 meters per second. We need to know the height, which by that time was 0.75 meters. We already know gravity, which is a constant, and we know the density of water is 1,000 kilograms per meter, per cubic meter. So, and we know atmospheric pressure is equal to this 101,325 pascals. So we put pressure, which is equal to 1,000 kilograms meter, 1.747 squared divided by 2 minus, sorry, this is meters per second. So all the units fit. Minus 9.8 meters per second square times the height at the moment, 0.75 meters, plus atmospheric pressure. The result of this operation, we already did it, and it is 501 pascals. So with this number, we now know that the pressure inside here was decreasing, and it was it couldn't the cap couldn't hold on, and that's why it imploded. Something interesting to see is that after the implosion of the cap, we obtained the second after we obtained that the velocity was equal to around 3.5 meters per second. And if we, this was our experimental velocity, but we could check if this is correct. How could we do it? We should use this formula. This formula comes from, I'm going to erase this because I need to explain you that this formula comes from velocity is equal to the square of 2 times the gush pressure divided by the density plus 2 times GH. Yeah, right. But since gush pressure is now atmospheric pressure minus atmospheric pressure, because it is not sealed, so this pressure is the same as this one. We get this formula, and if we put values to it, what we get is that 2 times the square root of 9.8 meter second square times 0.75 meters is equal more or less to 3.8 meters per second, which gives us around a 10% error, which is all like pretty good because it's all experimental. So I think that our experiment really worked.
We could conclude that the gauge pressure varied through the time, depending on the volume occupied by different fluid inside a system. Particularly in our experiment, we noticed how vacuum, which is simply a lower pressure compared to the atmospheric pressure, was created because as the water was coming out, the space was not filled with more air. Instead, the amount of air remained the same as the volume decreased.